Everyone. The authors could not be here, so they asked from us to have a presentation on behalf of them. So I'm going to present a video of them, and afterwards we will try to connect via Skype. And if we manage to, then you could ask some questions. So.
Hello, my name is Grigorios Tsoumakas, and today I will talk about discovering and exploiting deterministic label relationships in the context of multi-label learning. This is joint work with my former master student Christina Papagiannopoulou, now a PhD student in the University of Ghent in Belgium, and with Professor Ioannis Tsamardinos from the University of Crete and from the Foundation for Research and Technology Hellas in Greece. We apologize deeply for not being able to attend due to financial complications in our country, and we would like to thank Georgia Koloniari and Alexandros Karakassidis for their help in the poster session and with this presentation. We examine entailment relationships among the labels in a multi-label learning task. So, for example, consider two labels A and B. For these two labels, there are two positive entailment relationships among them. A entails B, and B entails A. There is also the exclusion relationship. A entails the negation of B, and the coexhaustion relationship, where the negation of A entails B. Our work focuses on positive entailment relationships between pairs of labels and mutual exclusion relationships among two or more labels. For extracting relationships, we examine the contingency table for each pair of labels. So here, S plus T plus U plus V equals the number of training examples. A entails B is extracted when U equals 0, and B entails A is extracted when T equals 0. In both cases, the support of the extracted relationship is equal to S. Mutual exclusion among labels A and B is extracted when S equals 0, and the support of this relationship is equal to T plus U. Relationships among more than two labels are extracted following the principles of the a priori algorithm. As a toy example, consider a multi-label dataset with 6 labels and 10 training examples. Here we can extract the positive entailment A entails B with the support of 3 examples. We can also extract A entails C, again with the support of 3 examples. B entails C is also extracted, in this case with the support of 5 examples. And finally, D entails C is extracted again with the support of 3 examples. We can also extract the mutual exclusion among labels A, E and F, which has a support of 9 training examples. We employ deterministic Bayesian networks for the exploitation of the relationships. So A entails B corresponds to a deterministic network where A is parent of B. The probability of B being true is equal to 1 when A is true and equal to 0 when A is false. When several labels entail B, we can generalize, and all of these labels become parents of B, while the probability of B being true is equal to 1 when at least one of its parents is true and equal to 0 otherwise. We further introduce a leak node in order to cover other causes of B. This corresponds to a virtual label which is true when B is true and all of its parents are false, and false in all other examples. To exploit mutual exclusion among K labels, we introduce a common child for all of these labels and reserve the evidence that this child is true. The probability of this child B being true is equal to 1 when only one of its parents is true and equal to 0 otherwise. As before, we introduce a leak node so that the relationship covers all training examples. This virtual label is true when all other parents of B are false, and false in all other examples. Preliminary experimentation showed us that the introduction of leak nodes leads to improved results. Continuing our toy example, the four positive entailments and the mutual exclusion relationships that we discovered among labels A, B, C, D, and F result in the deterministic network you see on the right, where the conditional probability tables of the nodes contain only extreme probabilities, 0 and 1. Let's now see an example of probability updates by our approach. On the table you see on the left, the middle column contains probabilities as obtained by a Bayes multilabel model. We can see that these probabilities violate the extracted background knowledge. For example, the probability of node B should be higher than the probabilities of node A and leak A that entail it, but this is not the case here. Similarly, the probability of node C should be higher than the probabilities of B, D, and leak D, which again is not the case. And also the probabilities of F, E, A, and leak EFA should add up to 1, as these are mutually exclusive and exhaustive labels, but again this is not the case. So what we do is that we insert these probabilities as soft evidence in our network, and after inference we obtain the updated probabilities that you see on the third column. And we can notice that these probabilities now satisfy the background knowledge. So the probability of B is now larger than A and leak A. The probability of C is larger than the probabilities of B, D, and leak BD. And the probabilities of A, F, E, and leak EFA add up to 1. A number of approaches considered the extraction and the exploitation of deterministic relationships in multilabel data. The approach by Park and Furkans was the first to consider the problem and employed association rules for discovering the relationships, plus an approach to correct the ranking of the labels with minimum changes, but the results were unsuccessful. The approaches by Mbagna et al. Were heuristic and did not adhere to some sound probabilistic principles. Perhaps the approach most similar to us is that by Baruchoğlu et al., published in Bioinformatics in 2006, where they employed the Bayesian network plus some given positive entailment relationships in the form of a directed acyclic graph. So they did not consider exclusion relationships, and they did not discover such relationships. Baumgartner's approach is theoretical and assumes that relationships satisfy all training examples, which is not the case with real-world data. The approach by Lochamessia and Janssen does not deal with probability correction and only looks at positive entailment relationships, plus it is limited to a specific learning approach, that of rule learning. The most theoretically appealing method is that of Deng et al., which was developed in parallel with us. It focused on a single computer vision dataset, and it employed a conditional random field plus an efficient inference process. There are also several approaches that consider probabilistic relationships among labels and multilabel data. And here you see some of these approaches. Some are based on Bayesian networks, like ours, some on multidimensional Bayesian networks, and others on conditional dependency networks. We experimented with our approach on 12 datasets. For relationship discovery, we set a minimum support of 2 training examples. In some cases where we ran into memory issues due to large number of mutual exclusion relationships, we increased the support exponentially until the problem was resolved. We employed binary relevance as the base multi-label model with a random forest of 10 trees per label using the Weka and Mulan libraries. We used the clustering algorithm for inference using the JSmile library, and we applied 10-fold cross-validation. Relationship discovery and exploitation was based only on the training set, but we also discussed some actual relationships that were discovered based on their presence on all folds. Positive entailment relationships were extracted in 7 out of the 12 datasets we considered, and we see these datasets in the first column of this table, and the average number of relations extracted in the last column. We report performance in terms of mean average precision, MAP, a popular measure in information retrieval, which is probably the dominant application of multi-label learning. This measure concerns all labels, but the relationships concern a small number of labels. This justifies the small improvement in mean average precision that we consistently notice in all datasets. Applying the Wilcoxon signed rank test, we find a p-value of 0.0156, indicating that the improvements are statistically significant at the 95% level. Mutual exclusion relationships were extracted from all 12 datasets, in some cases indicated with magenta in the third column, after increasing the minimum support to deal with memory issues. In 8 datasets, improvements were noticed. These are indicated with green font color in this column, while in 4 datasets with red font color again in this column, the mean average precision was reduced. The Wilcoxon test in this case indicates a non-significant difference, though by a small margin at the 90% level. We notice that in some datasets, here in the last column with cyan, 3 out of the 4 datasets where performance losses were noticed, the number of relationships is quite high. So we experimented with them with exponentially higher minimum supports, and the results show that gains can be achieved or increased where gains were already noticed, indicating that losses were probably due to spurious relations. So eventually, as in the case of positive entailments, improvements can be obtained consistently for all datasets, in the case of mutual exclusions too. This graph shows in the horizontal axis a range of minimum supports for the ImageClef 2001 dataset, and we can see that higher minimum supports reduce the number of rules, as indicated by the green line here and the green scale here at the right. And we also see that performance increases, mean average precision increases with the increase of minimum support, but if we continue increasing the minimum support a lot, then performance deteriorates again. Comparing positive entailments with mutual exclusions, we notice that the latter lead to larger improvements, probably due to the higher number of relationships and the corresponding higher number of affected labels. The graphs underneath show that the percentage of improvement is positively correlated with the number of extracted relationships divided by the number of labels. In other words, the more the relationships and the less the number of labels, the higher the improvement. This is an expected finding. Exploiting both positive entailments and mutual exclusions, results are improved in 4 out of 7 cases, as can be noticed here with the magenta in the last column. In the other 3 cases, positive entailments alone lead to better results. We now will see a sample of the discovered relationships. In ImageClef 2011, 27 entailment relationships were extracted from 8,000 examples. We can see here some obvious relationships, such as types of animals, types of vehicles, types of plants, types of water areas, and that clouds entail sky. There are also some less obvious relationships, such as desert entails day and horse entails day, as well as sea, lake, desert, and horse entail outdoor. There is also one relationship here that has a very high support, that female entails male, indicating that women cannot do without men. The medical dataset contains radiologist reports, and here 3 entailment relationships were extracted from 978 examples. And a Google search for the terms in the first relationship resulted in a page that verified this relationship. Emotions is a dataset about emotions evoked by hearing songs, and the exclusion discovered here concerns 2 emotions that are actually opposite to each other in the Thayer's model of emotions in terms of the arousal axis. So this is an expected relationship. And in the famous Enron dataset, the relationship concerned the concepts company business strategy and friendship affection, verifying that there is no room for affection in the business world. In the Internet Movie Database, 15 mutual exclusion relationships were extracted, 9 concerning pairs of labels, and 5 concerning triplets, and 1 quad. Some of these, such as a film noir comedy or a reality about war, could offer inspiration to innovative or provocative producers. To conclude, we developed a framework for the discovery and the exploitation of deterministic relationships among labels. Discovery is based on simple statistics and association rule mining principles, and there is here a need to statistically validate the discovered relationships in order to prune chance artifacts. We use deterministic Bayesian networks to exploit the relationships. Probability updates lead consistently to improved ranking of examples per label, as well as improved partitions, particularly based on the mutual exclusion relationships. Label rankings are distorted, as label probabilities are no longer comparable across all labels. This raises the need for a model addressing the full joint distribution of all labels, similarly to the approach by Deng et al. So that was all. Thank you very much for your attention. And again, apologies for not being able to be there with you. I will now try to connect with you to answer questions, and if that doesn't work, I will be available in the next 15 minutes via Skype and Google Talk in the addresses you see here, and of course we will be available, all of us, via email anytime. So thanks again.
Does anybody have a question?
Yes, we are trying now to call and connect via Skype, so yeah. That's probably not good. Maybe there are no questions right now. So, if there are any questions, you could individually try to contact the authors via the Skype addresses, via Google addresses. Now, I think we are connected. Good afternoon, Grigorios. Can you hear us?
Hi, can you hear me?
Okay.
Yes, I can. Say hi to everyone.
Any questions?
So, are there any questions here? Yes, I will just repeat the question because there is no microphone. Okay, so there is a question asking what's the future of this entailment relationship, if I understood correctly, right? And what we can use it for.
Sorry, Alexander, what is the future of?
What can happen after this entailment relationship? What can happen afterwards? how can we use it for?
Okay. Okay, so I guess you have already seen one way that this type of relationship can be exploited, so for correcting the probabilities. And another direction in the future would be to accelerate inference. So, for example, you can prune some of the shared space of the inference, some combinations of labels that should not occur according to the extracted relationships. Okay?
Okay. Okay. This concludes our conversation. Goodbye, Grigorios.
Okay, bye.